Okay, welcome back. So in the last lecture, we have talked about the selection and projection for U. And besides them, we also have another basic operation. It's called product of relations. So the product of relation is defined based on a set product actually. I hope you still remember what is a set product, right? Let's assume we have two input relation, R1 and R2. R1 has a schema with A1 to AN as the attributes, and R2 has B1 to Bm as the attributes. And we want to compute the product between R1 and R2. Then the question will be, what will be the output? First, we know the output will still be a relation, right? It is still a relation. However, what about the schema of the output relation? We can formally represent the schema of the product between R1 and R2 as S. S is another relation, is the output relation, right? For the S, it has A1 to AN and B1 to Bm as the attributes. You see this, right? In other words, we combine all the attributes from the two input relations to compose the output relation. A1 to AN and B1 to Bm. So it's about product between two relations. You see, this product can be very expensive because the output relation will be a very big table, right? This is about schema. You may wonder, how about the data tuples? For data tuples, we may have to combine all the instances in R1 with R2. It will be very similar to the set product we showed before. Right? You see, this operation is very expensive because the output table will be very huge in both the rows and the columns. Therefore, because this operation is expensive, it is seldomly used in practice. We don't use this product very often. Instead, we prefer to use the joins to help us. Join is more efficient in terms of the cost in both time and space. However, join is actually a more complex operation defined based on the product together with the selection and projection. We will show later. Let me provide you with an example about the product between two relations. Let's assume we have two relations. The first one is the employees, right? Employee has SSN and name as attributes. Another relation we have is a dependent. Now for the insurance, right? If you still remember, it's some work-ended sets. Dependent depends on the employees. Therefore, inside this dependent table, we have both the employee SSN together with the dependent name as the attributes. And here we plan to calculate the product between employee and dependent. So to represent the output, the first step is to decide the schema of the output relation. We know the output will be still a relation, right? It can be denoted by a table. It will have four attributes: SSN, name, as well as employee SSN and dependent name, right? We will combine all the attributes together. We will have four attributes in the output relation, right? Then how about the data tuples? For data tuples, we may have to combine all the tuples in this table with each one in the dependent table. In other words, for the annex records, we have the copies here, and the annex records we need to combine with both Chris and David, right? Here we have annex combined with Chris, annex combined with David as shown in the second row. And we may also have to combine the Brandy with Chris and Brandy with David as well as shown at the bottom. Alright. So you see the output table will be very huge if we have more attributes and more data tuples. Okay, let's assume we have a question like this. Given two relation tables, we have R1 table. The R1 table has A rows, A is the number, and N columns, N is also a number. Here I need to clarify that A denotes how many tuples we have. It doesn't count as the first row denotes attribute names. It doesn't include this one, right? And for the R1, the A will be equal to 3, right? We have 3 tuples. The N will be equal to 2, right? We have 2 attributes. This is just one example. And let's assume we have another relation table, R2. R2 has B rows and N columns. Then the question will be, what will be the dimensions or size of a new relation R3 equals to R1 times R2? How many rows and how many columns will we have for the R3? And you can pause here if you want to think about this. We will release the answer very soon. I hope you have an answer ready on your papers, right? So according to the definition of relation product, we know that in the output relation for the schema will combine all the attributes from the 2 input relations, right? If we have R1 with N columns and R2 with M columns, we know by combining them together, we will be able to define a schema for the R3, right? Therefore, by combining them together, we mean we need to sum them together, right? In other words, for the R3, the columns number will be equals to N plus M, right? So this denotes the columns we have for the R3 as the output. Then how about these rows? Remember we mentioned in the output relation, we need to combine all the tuples we have from R1 with R2, right? In other words, for the first record, we combine with this B rows, right? Same for the remaining ones. In other words, for the rows in R3, the number of rows will be equal to 2, what? 2A times B, right? I hope you have a right answer on your paper, right? It will be helpful for you to follow what does this mean for the product. So we see the product, the output relation will be very huge. I mean, the table size will be very big. If we have lots of rows in both 2 relations, then the A times B will be very big, right? For example, if we have 1 million rows in R1 and 1 million rows in R2, if we calculate the product between them, this number is beyond the limitation allowed for lots of machines. So please be careful. This operation is very expensive. Don't use this very often, especially for large tables. Okay, so this is about the product. And let's come back to the slides. Besides the projection, selection, and the product, we may also want to introduce another operation. It's called renaming. So the renaming doesn't do any changes to the data we have in the database systems. The only change it makes is to the schema. So the renaming doesn't change the relation instances. It can be formally represented as a row and with a subscript as B1 to Bn. This S denotes a new name for the relation. This B1 to Bn denotes a new name for the attributes. And we are working on a relation R as shown here. So you see, this operation will do the changes to the relational schema only. We have an input relation R with A1 to AN as attributes, right? However, right now we plan to make some changes to the names instead. We want to change this R name to S. We want to change A1 to B1, the name as well as AN name to BN name. So you see the output schema will be different from the input schema, right? Even though they contain the same information. However, the relation has been changed in both the names of the relation as well as the attributes inside the relation, right? So we provide an example about the renaming in the bottom. Let's assume we're still working on the employee table. And for the employee table, we have 2 attributes, the SSN and the name. However, later on we find that this relation is not very good, and we plan to make some changes to it. And then we can do the changes by using renaming, right? Here we don't want to change the relation name, we only plan to change the attribute name. We can do so by writing the row social security number, comma, first name on the employee relation. Right. In this way, we can change the attribute name in the employee relation. We change the SSN to the social security number. We change the name to the first name. Here, different from what we showed before, we do not provide the S here. In other words, we will still keep the employee as a new relation name. The S will be still the employee, right? And we can get a new employee table. We have two attributes. The first one is a social security number. The second one will be the first name, right? And for all the data tuples we have in the original table, they all be moved to the new table with no changes at all, right? We still have 3 data tuples as shown here. So the only change to make here is on the attribute names. And sometimes we can also make some changes to the relation name as well by providing the new relation name before the attributes in the row and the subscript, right? So you can do this by yourself on your papers. This is about the renaming. So far we have introduced different basic operations we can use on relations, right, to design queries. And based on these basic operations, we can define more complex operations, which are also called the derived operations. And in the following slide, we plan to talk about these derived operations for you. And the first one I'd like to introduce is for the set operations we can derive based on this union and difference. So we already mentioned this page before, right? We say this intersection and complement can both be derived based on this union and the difference. So the intersection denotes all the tuples existing in two relations, right? Which can be represented as this R1 cap R2, right? And for the intersection, it can be defined based on the difference, right? We mentioned before, the R1 cap R2 equals to R1 minus parentheses R1 minus R2. I also gave you a exercise to prove this equation holds, right? Since it is defined based on the difference, therefore we also have some requirements for this R1 and R2 as inputs. So the R1 R2 should have the same schema, right? So this intersection can work on two relations with the same schema. This is a prerequirement. As for the output of R1 cap R2, the output is also a relation, and this relation also has the same schema as the input, right? Besides intersection, we can also define some other derived operations. The most important one will be the joins. Join is a new operation we can define based on the basic operations. So formally, join denotes a combination of two tables and also selects some tuples meeting our requirements. How can we represent the joins? So we can represent the theta join first. It's a type of join with some conditions. Formally, we can represent theta join as R1 joins with theta denotes a condition. Theta is a join subscript here. Theta joins R2, right? So the theta here is a predicate. In other words, it denotes a condition, right? And R1, R2, there are two input relations. So we have the input schemas R1 with A1 to AN as attributes. We have R2 with B1 to BM as attributes. Then how about the output? The output will also be a relation, right? We can represent the output as a relation S. As to the attributes inside this S, we have A1 to AN and B1 to BM. We combine all the attributes in both R1 and R2. So what does this theta join means, and how to derive it based on the basic operations? So formally, we can define the theta join as sigma theta as a condition, and we are working on this R1 times R2. So you can see we do the product between R1 and R2 first, and then we can further do the selection on some conditions. This condition is defined by the theta, this predicate. Therefore, we say this theta is also condition before, right? Because we use the theta here for the sigma as a condition. We have sigma theta, the condition, which is a subscript, and parentheses. Inside the parentheses, we have R1 times R2 as the relation we're working on here. So therefore, when we are working on the theta join, we can take the product of R1 and R2 first, and based on the product relation, we can further apply this selection to select some tuples meeting our requirements. In this way, the output relation, the schema, the output relation will be much smaller than the product, right? Before we mentioned this product can be very expensive in both time and space cost. However, if we do some selections here, then we can shrink the dimensions, the rows in output, right? And the columns still remain the same. It is the same as the product of this two relation, the number of columns in the output. So for the C here, we can use all the conditions we defined before, right? It can return some Boolean values as a condition. So this is theta join. Theta join is very important, and it can be very helpful for you because in the future, almost all the operations or the queries, we will be working on multiple relations and tables simultaneously. Then we have to join them together with the theta join to help us. So this is the definition of the theta join. You may also wonder, can we have any concrete examples so it will be helpful for you to follow the ideas, right? And we show the theta join example in this page. Let's assume we have two relations. The first relation we have is bars. We have a bar here. The bar has two attributes. The first one is bar name. The second one is the bar address. In the bar table, we have two tuples. The first one is ages. The second one is Michael's pub. Besides the bar, this relation, we also have a sales this relation. Right? The sales relation has three attributes: bar name, beer name, and the price. It denotes the price for the bars to sell some beers. And inside the table, we have four data tuples: the ages, sales bud, ages, sales minor, and Michael's pub sales bud, and Michael's pub sales corona. And we also show the price for the beers, right, sold by the bars. And then we have a theta join query. We want to calculate the sales theta join bar with the condition the sales dot bar equals to bar dot name. In other words, we want to join the two tables together and also select the tuples with this bar name matching the sales bar, this name here. According to the theta join definition, we need to calculate the product between bar and sales first, right? By calculating this product, we will get another table. The table will have 5 columns we showed before, right? We know this number of columns will equals to 2 plus 3, right? We have another table. And how many rows do we have? We need to combine all the rows together, right? If we calculate the product first. In other words, the number of rows will be 2 times 4 will be 8, right? And based on the product between these two relations, we further apply the selection based on the condition that sales.bar equals to bar.name. In other words, among them, we further do the selection to select some rows, and we can represent the result at the bottom. The schema will be the combination of all the attributes for bar and sales, right? We have bar, beer, price from sales table. We have name, address from bar table, right? And for the data tuples, before we mentioned, if we calculate the product between them, the number of rows will be 8. 2 times 4, right? However, if we further apply the condition for the selection here, then we can further prune some rows and also delete the remaining ones. And we can check the remaining rows we have in the table. Each row denotes a data tuple, right? And we check the bar name. We check the cells bar versus by name. We find that each one they are equals to each other, right? HH, microspop, as well for the remaining one, right? So this is about theta join. Theta join is defined by combining the product and the selection. If you can remember the basic operation that we covered before, then you should be able to follow the ideas we mentioned here very easily, right? So we do the product first and then further apply this selection.